Hey everybody, and welcome back to Algebra 2 online. So today we're going to kind of build off of what we talked about in the last video with the domain piece, and we're going to use that and start finally getting into solving these nth root equations. So the part that a lot of students make a mistake with is that related to like the whole domain part. So because these things are only defined at certain spots, you get some weird things where sometimes solutions that seem like they should be right are not actually correct, and they call those things extraneous solutions. So because of the weird domain issue with the even roots, you have to check your answers, basically. So to start off, though, I want to just kind of crank through some algebra here. So one of the things that we're going to see a lot is we're going to have to square something like this. So this is like just an expression built out of two square root functions, and squaring it can be kind of annoying. So I'm literally just going to square it out and then simplify it as much as possible. So you will have to do this in stuff on the homework, and we'll do it here in the video in a little bit too. So if I was squaring that, right, I'm just literally multiplying this thing by itself. Whoops, I don't know why I wrote negative there. 3 minus 4x plus square root 4x plus 1 times square root 3 minus 4x plus square root 4x plus 1. And some of it's pretty nice, because if you multiply out, I'm literally just double distributing, right? And I'll try and keep these things color-coded as I go here. But when I do, when I distribute this first one, I'm going to multiply it by itself right here. And when you square a square root, right, we know we cancel that thing off. So I get 3 minus 4x from the first distribution. The next one's not so nice. For right now, I'm just going to say I multiplied those two like that. Then the second distribution, now the first one's not so nice, but the second one would be nice, right? So I'll have plus square root 4x plus 1 times 3 minus 4x. And then I'll have a plus 4x plus 1, right? Because I've killed the square root again because I've squared a square root. So that's what the first kind of step there could be. And then I'm going to go ahead and start simplifying some stuff. So you have a minus 4x and a plus 4x, so that's actually nice, right? And then if you look here, I've got the same square roots multiplied. So I've got two of those, so I could combine those. And then I also have 3 and a plus 1, right? So I have 4 plus 2 of these square roots. And so you could leave it like that. That's fine. You also could certainly just, because whenever you multiply a square root by another square root, right, you can also just simplify it by putting it under the same square root, right? So I could just write that as well. And personally, I would take this one or this one. I don't really care. I don't really think one is more simple than the other one. But that kind of thing where you're going to square this kind of binomial of roots here, that will definitely pop up a lot in these problems. And I think a lot of times students struggle with all that algebra. But that's how we could take this thing and expand it and simplify it to that. All right, so basically the plan is just go through a few examples and kind of highlight the issues I sort of typically see with these root equations. My plan for these is always basically just to isolate a root, like some root function, because sometimes they actually could be mixed. You could have like a square root and a cube root, but just isolate a root function and then use inverse operations to solve it from there, right? And this middle kind of highlighted spot I got right here. So like I was saying before, the domain of these things and the fact that they're not like well-defined, those two issues that are associated with really even roots make it so that you can get things that are not going to have solutions, even though they look like they should. So you always have to check your answers, okay? So first one is kind of all done here. I have a root function isolated, right? It's by itself on this side. So the inverse operation to kill the square root would be to square it, right? And this is probably where you can start to see what I did in the last problem and why that shows up. So this side's nice and easy because I literally just killed that square root, get x plus 15. But on the other side, I'm going to square this binomial, and that's where I'll have to do like double distribute and everything, right? So if I do that, I would get 9 minus 6 square roots of x, and then plus x, because I had a double negative and squared square root, so I got rid of this square root. Then let's simplify a little bit. So this is kind of nice because I have an x on both sides, right? So they would cancel. And then 15 minus 9 is probably what we should do next, which is 6, right? So now we have 6 equals negative 6 square root of x. You could also divide by 6, right? I'm going to divide by negative 6. I think we'll do it that way. So I'm going to have negative 1 equals square root of x. And then you've got negative 1 equals square root of x, and you might be seeing where this is going at this point. You square again, right? And when you square again, you would have the answer, but you kind of also don't have the answer. So square negative 1, you get 1. So it's saying x is 1, right? And I think at this line right here is where you might have already seen that there's actually going to be no solution. So, we know that square root of x kind of looks like that, right? And we know that negative 1 is down here. And so this curve is not going to ever intersect that. So once I get to that point, I can already see in the problem, like, there's no solution. But that's what this highlighted thing up here is all about. You got to check answers. So you just take 1, okay, and you just go and plug it in really quick. You don't need to show this kind of stuff. I'm just going to show it here, just so you can see. So, you plug in 1, you'd get square root of 16, which is 4. But 3 minus square root of 1 equals 2, right? And 4, I believe, is not equal to 2. So we can see that there's actually no solution in this problem. And I wanted to also quickly show you a visual way to think about this problem. So if you think about it, the left-hand side, the square root of x plus 15, that's just shifting over, this kind of square root function like that. And then the right-hand side, 3 minus square root of x, right, that is like 2 transformations. That is taking, this is normally square root. It flips it upside down with the negative. So it flips it up, right? And then you add 3. So 1, 2, 3. So it's kind of doing that. So my picture, probably not perfect, and this is probably something I'll also show you in Desmos, but basically you've got a curve that's always curving up here, and then you got a curve that's always curving down. And so there's no way that this curve would ever intersect this curve. So there's no solution to this problem, right? That's like a visual way to do it. That's how I think about it. But the algebra, if you just crank through it, right, you get this x equals 1, which it wants to be a solution. But when you go and plug in 1, just check it, you see that it doesn't work, right? 4 is not equal to 2. So even though this visual way is kind of how I want you to think about it, it's always good to just be able to do this algebra too. So I actually kind of think you should be able to do both of those, but trust your algebra more so than your pictures a lot of times. All right, so this one actually will have an answer, and it's much more work, and I think it's probably about as hard as a problem you'll have on your homework that you could get. It's a little long. So I'm going to start, and I want to isolate a root, but I actually have just 3 terms with roots in every one. So I've already got one isolated on this side. So I can just hop right into, again, like the last problem, I just started by getting rid of the root. That's what I'm going to do first. I'm going to take both sides, right, and just square both sides. Maybe I'll say really quickly, one thing I see people do sometimes in these problems is they do this. They want to square that, and that. But that makes no sense because, you're doing something you know, an equation is just like a scale, right? And you're just saying that this side is balanced with this side. But what you've done is you've done two things on that left side and one thing on this right side. And so now you've thrown the scale off. It's like you don't have a balance anymore. So when you do operations in math, you do the exact same thing on both sides. A lot of times we don't write it. Like if we have 2x plus 1 equals 3, and we're looking to solve it, you know, really what you do is you subtract 1 on both sides, right? It's like you've taken this whole side and you subtract 1. Then you take this whole side and you subtract 1. I'm doing the same thing, except, you know, here I need to square both sides. So instead of minus 1 from both sides, because that wouldn't be helpful, I get rid of a root by squaring both sides. But don't think you can just because you see 3 roots, don't think that you can get rid of all 3. That's like a thing that I see sometimes students do, but it doesn't keep that balance that we need in the equation. All right, so square both sides. I'm going to flip things around. Nah, I won't flip things around. I feel like that's going to be too confusing. So I'm going to square out this part right here. And this is why I did that first example. I'm going to actually pause the video and just write down what you get from this part. And I'll do that in green, let's say. And then I'll do this other side in yellow. That side won't be bad, right? Because it'll just be 9, and it'll kill the square root. So 9 times a quantity of x minus 1. But this side is just like the first problem we did. And so I'm going to pause the video, write down what you get, and you should just check your work basically against mine. All right, so that is what we should get here. And you know, trying to color code everything. This left side is all in green here, and the right side's in yellow. And then we have these two terms, which we can combine with these, right? So I would get 2 times the square root of x plus 4, square root of 2x minus 1. And then I think I'm actually going to drop my color coding because now it doesn't matter. Then it would equal, 9 minus 3 is 6x, and then negative 9 minus 3 is minus 12. And so in an example like this, well, actually one thing I'm seeing, I got a 2, a 6, and a 12. Those are all even. I might as well save myself a little work and just divide out by 2. That's nice. So 3x minus 12 divided by 2 is 6. So now it basically just all starts over, right? So I've got roots isolate, like a root function isolated, which I could put this into one root, but it's really just one term, so it's isolated, right? And then you might as well just go and square both sides again, right? So if I do that, maybe now I will do this side in orange, let's say, and we'll do this side in blue, okay? And the left side now is the nice one, because if you square the square root, right, you just kill off the square root, so you have like x plus 4 times 2x minus 1. Now the right-hand side is the annoying one, because if you square that binomial, you'll have to like double distribute, right? And you'll get, if you do it out, you'll get 9x squared minus 36x plus 36. And so let's actually square out the left side too. So I'll have 2x squared plus, not square it out, but just multiply it out. And then I'm just going to copy that down. All right, so basically just morphed this root equation problem now into a quadratic equation, right? And if you just take everything and put it all on one side, I would personally move the orange stuff to the right. So I would get 7x squared minus 43x plus 40. That quadratic, not that nice. I would basically just do quadratic formula. If you go, I would definitely use a calculator for this kind of stuff. So negative b plus or minus b squared minus 4ac, right? All over 2 times 7. And if you do that out, I'm not going to show all that work because we've done that so many times here. You get 43 plus or minus 27 over 14. And one of those is 5, and the other is 16 over 14. And so, after all of that work, you probably just want to go and circle these answers and just be done. I don't blame you. It is a lot of algebra, but you can't. And that's because even root functions are annoying. They are annoying for two reasons. One, in order to even be a function, we deleted half of the graph. It's pretty weird. Talked about that. And the other thing is this domain issue. So to check which one of these work, right, the easiest way, if it's an equation, just go plug the numbers in and just see if your solutions really are solutions, right? So if you go and plug in, 5 for x everywhere and 16 over 14 for x everywhere, what you're going to notice is actually that 16 over 14 does not work, but 5 does, okay? So there's only one solution, and that just comes from that last check part. And I don't need you to do the check out. Like when I've taught Algebra 1, I asked my students to write out that check part, and I want to see all that. We're kind of beyond that stuff at this point. You can literally, I just would assume you want to get the problem right, and the last part should just be done on a calculator. You just go take this 5, you just, you get square root of 9 there, you get square root of, 9 again, and then 3 times square root of 4. But you just go plug it in and see if it works, and you do the same thing for that fraction 16 over 14, and you'll see that it doesn't work, okay? And that's kind of as messy as they get. I wanted to do one more problem, and it's a little different, but also actually much easier than this one. So, and that is this one. So the the root functions come in all forms, and we've seen that this 1/4 power is a root, right? This thing is really the 4th root of 3x plus 7, and then minus 3 equals 1. And so we can solve 4th roots, no different than we can solve square roots, okay? If it's just a different inverse function to solve the thing out, right? So in this one, same thing as the last problem. I want to isolate the root, so I'm going to have to add over that 3, and I get 4. And then the inverse function is what's different here. So before, squaring was the inverse function to get rid of square root. Now, raising to the power of 4 is what's going to do it, right? And so if I do that to both sides, you'll kill off the root, right, on the left, and you'll just get 3x plus 7. And then 4 to the 4th is, so what was I saying? So 4 to the 4th is 256, okay? And then just basically minus 7. That would be 249, and then if you divide by 3, that is 83. And just like square roots, really all even roots, you might as well check your answer. The ones that are actually weird are just the even roots, so technically you don't have to check your solutions if it's an odd root. They're going to be well defined basically everywhere, but the even roots, you always got to check. So if you just go and check this one, basically just do, right, 3 times 83 plus 7, all raised to the 4th, minus 3. We basically hope that is 1. And if you go and plug all that in, you would see that truly you get 1 on the left side. So it checks. So this 83 that we found is actually the solution. But yeah, so I just wanted to show you one where it was a different root rather than a square root. They're really not that different. The only part that's different is right there on that step in red. You just use a different inverse operation to unpack that equation. That's it.